So the big idea that we're going to talk about right now is the word congruent. The word congruent means it's the exact same size and shape. It's got the same angle measures and the same side lengths. Then two figures are congruent. So if you perform a reflection, a translation, or a rotation, they'll be congruent. Dilations or a stretch would not produce congruent figures. But reflections, translations, rotations, those are rigid motions. You get the same size and shape before and after. So, the first ABCD mapped onto EFGH. Are they congruent, and how do we know? So, yes, they're going to be congruent. The symbol for congruent is equals with a squiggle on top. Yes, they are congruent, and we know that they're congruent because there's a translation that would map ABCD onto EFGH. If you just translate A 4 to the right and down 4, and you do the same thing with B, 4 to the right, down 4, and then C, 4 to the right, down 4, D, 4 to the right, down 4. It maps perfectly onto EFGH. So you know that they are congruent because it is a translation. If you wrote that as a vector, 4 to the right, down 4. Do a similar concept here for JKLM. That will map onto PNRQ if it's reflected. You just got to figure out that line of reflection. I think it would be right about here. And everything will be equally spaced. So yes, they are congruent because it can be reflected over whatever line that is. We can't really name the line. So these two figures, they are definitely not congruent. To get from one to the other, it would have to be a dilation. So not congruent because that is a dilation. Everything, all the coordinates are being multiplied by some number. And dilations change the size and shape, unless the scale factor is 1. Dilations will change the size and shape. So these next examples, they are actually in the coordinates. So we can more easily describe the transformation. So it looks like they are the same size and shape. So you look for the rigid transformation, like a reflection, rotation, or translation, that's going to map one onto the other. And you can get that if you reflect over the y-axis. Everything will be equally spaced. So yes, they are congruent because you just have to reflect over the y-axis. Two figures appear to be the same. So how can we map triangle ABC onto XYZ? That looks like that would be a rotation. We're going that way, so that's counterclockwise. And that's just a quarter of a turn, so 90 degrees counterclockwise. Rotating is a rigid motion. So the two figures are congruent. So the coordinate notation is x comma y goes to negative y comma x. That's the rule for a 90-degree counterclockwise rotation. So both of these, they're both reflections. This number 2 here, that's a reflection over the x-axis. It's just a mirror image, same thing above and below the x-axis. And then number 3 could be a reflection over this line that splits down the middle of them. Since the graph is counting by 2, that means that will be at x equals negative 3. Reflect over x equals negative 3. So now we're going to step it up just a little bit, and now they're going to be a sequence of rigid motions. So it might be 2 or 3 of them strung together in a certain order to make sure that they map onto each other to see that they are congruent. So triangle ABC, to get it to map over here to PQR, there's, I think, a couple ways you could do it. You could get it as a rotation, 180 degrees, or you could reflect over the x and the y axis. Actually, a rotation of 180 degrees and is the exact same as a reflection over the x and y axis. It works out the exact same way. So it's a little bit less writing if I say rotate 180 degrees. Sorry if I'm getting right first. But it would not be wrong if you said reflect over the x-axis, then reflect over the y-axis. That would be okay. So if you rotate 180, that puts point C right here. Point A would be right there. And then B would be there. So to make that map perfectly onto the other figure, we need to translate it now just a little bit. Just to the right 1 unit, because we're going from a 2, it needs to map over here to a 3. So to the right 1 unit, doesn't have to go up or down at all. Next example, pretty similar. You could, in the order you do these two, that won't matter. You can reflect and then translate, or you could translate then reflect. It would work out the same way. You just have to use different numbers. So we can reflect over the y-axis. If you do that, you get K there. You get those vertices. And to get those to match up correctly, just pick one and count out what the translation would be. It needs to go up. Remember, we're counting by twos on this. It'd be 0, 2, 4, 6, 8. So it's counting by twos. So we're going up 2, 4, 6, 8, 10, up 10. And to the right, that'll be 2 units. Alternatively, you could have done the translation first. You would have had to move it a little bit to the left and up a whole bunch and then reflect. It would have worked out the same way. I prefer to save translations for the end. I think it's easier. Same idea. We can reflect this, starting with J, K, L, M, reflect it down over the x-axis. So that would reflect to there. And then we need to translate it. We need to slide it where it's supposed to go. And again, the graph is counting by twos. So if we're going left 2, 4. So that's a -4. And we have to go down. That'd be 2 units. Down 2 would be a -2. For the next one, looks like the figure is being reflected. So now we can get this side here, CB, to match up right there with RQ. So it's being reflected over the y-axis. So if we reflect that, that ends up, B would be there, C is there, A, there's D, E would come to this side, right there. Then we need to translate it down to where it's supposed to go. It looks like it just needs to drop straight down. So just count how far it needs to drop. Again, the graph is counting by twos. 2, 4, 6, 8. So you drop it down 2, 4, 6, 8, 10. We don't need to move it left or right, so 0, -10.